Alright, so we're just going to start up the simulation here. Should work on most browsers. And we are on Fission 1 nucleus. We have a uranium-235 nucleus here. And we have this neutron gun over here. You'll see when we press this button, it will launch a neutron. And then we'll watch what happens to the energy and what happens to the nucleus itself. The first question is, what can you do to make the nucleus unstable? Well, there's not too many things we can do on this particular screen, but one thing we can do is press this button. Fires a neutron, and what happens there? Let's try that again. Let's see if I can pause it. So see what you can see here. You're going to make some notes of your observations. There's a key over here that shows you what the different colored spheres represent. There's a graph down here showing energy. And then I'm going to roll that forward, but you can pause here if you need to make more notes. We'll do that one more time. Launching a nucleus at the uranium-235. There's the result. The next question is, now that we've seen what happens when you fire a neutron at a uranium atom or nucleus, what do you think would happen if we had a whole bunch of these nuclei and we fired neutrons? Keep in mind the results, what happens, what all the products of this breakup are, and try to think about, well, what would happen if we had a whole bunch of these atoms and one or even a few of them went through this process and there were a bunch more uranium nuclei around. The next question asks you to go to the chain reaction tab, which I'm going to do here. So initially we basically start out with the same thing we had before. We have the neutron gun, we have the uranium-235, we can launch it, reset, see what happens here. Same thing happens that we watched in the one nucleus. The difference here is we can reset, we can change the number of nuclei. Okay, so let's see what happens if we make this 0 and make this 1. Okay, now we have one uranium-238, which doesn't look like it's going to let us. We're not going to be able to hit that one. So we're going to reset. Now let's add more uranium atoms. We're up to 24. When we fire, we get that reaction. Reset. Do it again. It was a little different that time. Again, you can pause anytime you need to make notes. The question is asking you to describe a chain reaction. So I'm just pausing it here so you can see kind of where we are, and then let it run again. Now let's add some uranium-238. Let's see what happens when we have some of each. Well, the uranium-238 changed to uranium-239. It took the neutron and absorbed it. So that's what happens when we get a neutron that passes through until it hits a uranium-235. And you see the response here. You also can see, hopefully, that more of the uranium-238 has now become uranium-239. Let's see what happens if we decrease the number of 235 and we increase the number of 239. So the number of uranium-235 didn't change much. We didn't get as much of a reaction. You can see that the 238 has turned into 239 now. But when you turn the 238 into 239, it just sucks up and absorbs that neutron, as opposed to the 235, which breaks apart and spits out more neutrons, which can then go on to interact with other atoms. So I'm going to try starting with more 235 and then a whole bunch of 238. Okay, so by having the 238 in here, it takes up some of those neutrons and stops the chain reaction. Now what if we have a few 238s and a whole bunch of 235s? Just to pause here so you can see what's going on. You can see that the number of 235s has gone way down because so many of them have been hit by a neutron and they release their own neutrons and that hits the next atom and so on. So the 238s are converting to 239, but because there's so many more of the 235s, they're the ones that break up. They're also the ones that throw out more neutrons. So you get more neutrons to break up more atoms, and that continues the reaction. The question in the packet is, why is uranium-235 such a good material for creating a chain reaction? So you can kind of see that here. Let's reset and watch again. The 238 absorbs the neutrons, and then when we hit a 235, it releases more neutrons, which can then interact with other atoms. And that's how we get the chain reaction. The next question is about what would you want or need in order to make an effective bomb, nuclear bomb. So you should have researched how the atomic bomb works, or an atomic bomb works, keeping in mind that the only material we have here is uranium, 235 or 238. One of the things we know we need is a whole bunch of uranium. But does it work if you have any type of uranium? As we've seen before, uranium-238, if you hit it with some neutrons, just becomes uranium-239. So would that be an effective material for making a bomb that you want to have an uncontrolled chain reaction take place? Let's reset. Now let's try it with all uranium-235. If you want to create an uncontrolled chain reaction, this might be what you want. A significant amount of concentrated uranium-235. The final portion asks you to go to the nuclear reactor tab. So we have the reactor here filled with uranium-235. As we saw on the previous tab, if you hit a uranium-235 atom with a neutron, it breaks apart and releases more neutrons along with some other things and some energy. And if you have a lot of uranium-235s together, when one breaks apart, the neutrons from that nucleus hits the next nucleus and breaks that apart, which releases more neutrons, and you can get an uncontrolled chain reaction. The thing that we have here in the reactor is these things called control rods, which are heavy, dense metals that will absorb some of the neutrons. So if we fire a neutron, you can see in this chamber here we're getting a chain reaction to an extent, but it's also not, for the most part, moving into any of these other chambers. There was a little bit of reaction here, but it went out very quickly. If we fire more neutrons, you can get more reaction. Each time you do that, you're getting a certain amount of power output and energy. Now if we reset, there's a question about what is the purpose of the control rods. Well, as you might see from the name, it's to control the reaction. So if I move these down, so now I've opened up some space between these chambers. I still have some control here. And I start firing in neutrons. Now you can see some of the reaction is spilling into different chambers. You're getting more output, you're getting more energy, and it's continuing. And you see the temperature in the chamber is going up here. Okay, so now that has stopped for the moment. So let's reset. What happens if we take the control rods completely out? We're producing a lot of energy, but we're also generating a lot of heat. We're using up all of this material. And you can see that we are producing energy, but we also did produce a lot of heat. It's going down now because the reaction is dying out. But let's reset and try again. When this heat gets too high, this is when you have what we know as a meltdown in the reactor. It can overheat and actually melt the reactor, and that releases the radioactive waste, radioactive material into the environment. So we're going to reset. You get a lot of energy very fast, but you have, in some respects, the same thing that we had when we were trying to make the nuclear bomb. You have concentrated uranium contained in a space and an uncontrolled chain reaction. So we reset, we put the control rods back, and you can see we get very short-lived reactions, and they're fairly well contained within each chamber. These control rods aren't going to stop every single neutron, but their job is to slow down or stop enough of them to control and limit the rate of the reaction. So you could certainly use these control rods as a tool to regulate how much energy you're putting out. Let's say the demand for electricity goes up. Well, we could lower these control rods a little bit, and we should get a little bit more of a reaction. Lets it go from one chamber to the next and produces more energy. The more you lower them, the more energy you should get. The more chambers get involved, the more output you have. Also, the more heat that you generate in the reactor. You put the control rods back and the reaction dies out.